Hi, in this part of the lecture, we are going to talk about how we can improve the efficiency of the VCR cycle. We are going to talk about the Cascade VCR cycle in this part. The Cascade VCR cycle can be used to improve the efficiency of the VCR cycle. In the case where we have a large temperature difference between the warm environment and the cold refrigerated space. Okay, if we have a large difference in TH and TC, okay, temperature between them are very wide. Okay, now you can see that instead of using a single VCR cycle, we are now using two cycles here. In this case, we have cycle A and cycle B. Okay, cycle B here will be used to absorb the heat from the cold refrigerated space. But instead of rejecting the heat to environment, it will reject the heat to the evaporator of cycle A, which is on top here. Okay, and the heat rejection from cycle A will be rejected to the warm environment in this case. Okay, so you can see you have two cycles operate in a cascade manner. Okay, one on top of the other one, A on top of B, like this. Now you can see the benefit of using the cascade cycle by looking at the TS diagram here. Now you can see that cycle from point 1, 2, 3, and 4 here is the cycle B. Okay, this is cycle B. And cycle starting from 5, 6, 7, 8, this is cycle A. Okay, you can see that if we don't use the cascade cycle, but rather we use just single VCR cycle, the single VCR cycle would be this one, this cycle. It would be from 1, okay, and we compress to a high pressure, okay, temperature, and then we reject the heat through the condenser, okay, like this, and then we flash, okay, from the sad liquid until it had reached the lowest pressure here and absorb the heat again in the evaporator and then continue the cycle. So you can see that if we compare between the cascade cycle and the green cycle, which is a simple VCR, okay, simple VCR here, right? You can see that we can see some difference between the area inside the cycle. You can see the pink area here. The pink area is the area which is the difference between the simple cycle and the cascade cycle. You can see that the cascade cycle will have less area than the simple VCR cycle. Less area means decrease in compressor work. So it means that in the cascade cycle, you will require less shaft work for a compressor. Okay. Now, when we compare between the cascade and the simple VCR, you can see that for simple VCR, you have a refrigeration capacity of this amount. Okay, the width here represent the refrigeration capacity of the single VCR. This is for simple VCR. But here in the Cascade VCR, you have an increase in the refrigeration capacity. Okay, you can absorb more heat. This is the refrigeration capacity of the Cascade VCR. Okay, so you can see that you have obvious benefit in terms of the increase in the refrigeration capacity when you change from the simple VCR to the Cascade VCR. Okay, so you have two direct benefits here. You will require less amount of compressor work, and you can increase the refrigeration capacity in the Cascade VCR here. Now, you can see that the picture that I have shown you on the TS diagram here is called the ideal cascade cycle. Ideal cascade cycle. Okay, ideal cascade cycle means that the compressor inlet would be at sat vapor, okay, and the condenser outlet would be at sat liquid, which is number 7 and number 3. And for ideal cascade cycle, it means that we assume there is no temperature difference in the heat transfer between cycle A and cycle B. So it means that you can see in this area, okay, 825 and 223 here, it would be at the same temperatures. There would be no temperature difference. Okay, heat transfer with no delta T. Okay, no temperature difference. So this is the ideal case. But in the actual cycle, okay, in the actual cycle, you might see that you have a cycle which may contain some irreversibility. For example, number 1 may not be the sat vapor, it may be superheated vapor. Number 1 to 2, which is compressor, it may be irreversible compression. Okay, number 3 here, okay, it may be subcooled liquid rather than sat liquid. Okay, now you already know that for cycle B, it will transfer heat to cycle A. So in the actual heat transfer, you must have some temperature difference between the hot stream and the cold stream. So cycle A would have to be located like this. It means that you must have some temperature difference to have possible or feasible heat transfer between cycle B to cycle A, like this one. So the temperature of the cycle B must be higher than the temperature here at this point in cycle A. Okay, so it means that 2.2 to 0.3 would have to be at higher temperature than 0.8 to 0.5. So this is the actual cascade cycle. Okay, now you can see that the heat transfer in the heat exchangers, if we draw the diagram or draw the temperature profile on TQ diagram, you will see that cycle B from number 2 to number 3 will transfer heat to cycle A from number 8 to number 5. Okay, this is the Q cascade. So you can actually do the heat balance, okay, between the Q hot and Q cold. They must be equal. Okay, so you have MA H5 minus H8. This is Q cold, and that must be equal to MB multiplied by H2 minus H3. This is Q hot. Okay, Q hot equal to Q cold. Heat transfer from hot stream equal to heat absorbed by the cold stream. Okay, So you can see that the enthalpy change on each side are not equal. H5 minus HA is not equal to H2 minus H3. So it means that the mass flow rate in both cycles must be different. It means that MA and MB are not equal. Okay, so you can determine the mass flow ratio between these two cycles by using the result from the energy balance in the heat exchanger here. MB over MA over MB equal to H2 minus H3 divided by H5 minus HA. Okay. And the COP of the overall cascade cycle can be calculated from the same definition that we have learned before. It would be what we get divided by what we give. What we get would be QL. Okay, QL is the heat absorbed. Heat absorbed or heat removal, okay, from cold refrigerated space. Okay, heat removal from cold refrigerated space. So the cycle that is used to remove the heat from the cold refrigerated space is cycle B. So QL is equal to MB multiplied by H1 minus H4. Okay. So you can see that we use the equation in the rate form, in the heat transfer rate, in the work transfer rate, because the mass flow at any particular location are not the same. Okay. Divided by W net in. W net in, you have to supply work to both compressor of cycle A, that would be MA multiplied by H6 minus H5, and work required for cycle B, MB multiplied by H2 minus H1. Okay, so you have the work required for two compressors. Okay, and QL is the heat removed from cycle B only. Okay. Now let's have a look at the example on the cascade refrigeration cycle. Okay. Now consider a two-stage cascade refrigeration system is a two-stage. Actually, we could have more than two stages. We may have 3 or 4 stages, okay, in cascade. Okay. They operate between the pressure limit of 0.8 and 0.14. So it means 0.8 is the highest pressure, 0.14 is the lowest pressure value. Each stage operates on an ideal vapor compression refrigeration. So you have seen the keyword here, ideal. So it means that the compressor inlet would be sat vapor, condenser outlet would be sat liquid, and all process would be isentropic, isobaric, isenthalpic in the valve, and isobaric in the evaporator again. Okay, so you can just draw the cycle A and cycle B here like this. Okay, when you see the word ideal, it means that the heat transfer in the heat exchanger between cycle A and cycle B will have no temperature difference. So it means that the heat transfer here occur at the same pressure. Okay, it would be at the same pressure level. Okay, one condensing, the other one evaporating. Okay, same pressure level here. The refrigerant that we are using is refrigerant R134A, is our working fluid. The heat rejection from the lower cycle, to the upper cycle take place in an adiabatic counterflow heat exchanger. Okay, and it occurs at 0.32 megapascal. Okay, both stream exchange the heat at the same pressure, so the temperature would be the same in the two-phase region here, 0.32 megapascal. And we already know that in practice you cannot have this kind of situations. The working fluid of the lower cycle must be at a higher pressure and temperature in the heat exchanger to have a feasible heat transfer, have an effective heat transfer, as shown in the previous slide. Okay. Now what we want to know is that if the mass flow rate of the refrigerant through the upper cycle is cycle A, okay, is 0.05 kilogram per second. We want to determine the mass flow rate of the refrigerant through the lower cycle. So we want to determine MB dot. Okay, we want to determine MB dot. Right? We also want to determine the rate of heat removal from the refrigerator space and the power input to the compressor. It means we want to determine QL dot and W net in dot as well. And lastly, we want to determine the COP of the cascade system here. Okay. Now in these problems, it's rather easy because the problem already gives you the enthalpy value at every point. You have H1, you have H2, you have H3, and H4 is equal to H3 as well. You have H5, H6, 7, and 8. You have enthalpy value at every point. So you can just doing the energy balance to calculate the parameter that you want to know. Okay. Now let's start with the determination of the mass flow rate of the refrigerant in the lower cycle or in cycle B, MB dot here. You can find MB dot from the energy balance around the adiabatic heat exchanger. Okay, so in the heat exchanger, okay, you may draw a simple diagram of heat transfer between them. Okay, you have 2 to 3, okay, and exchange heat with 8 to 5. Okay, 2 to 3 transfer heat to 8 to 5. 2 to 3 would be with the mass flow rate of MB dot. Okay, 8 to 5 would be with the mass flow rate of MA dot here. Okay, so if you do the energy balance around the adiabatic heat exchanger here, you can write energy in equal to energy out. Okay, energy in will be the energy coming in with the inlet stream. So you have MAH8, okay, plus MBH2. This is the inlet stream. Enthalpy coming in with the inlet stream flow. Okay, and that would be equal to energy going out with stream number 3, MBH3 plus MAH5. Okay, now you can rearrange this equation and then substitute the value that you already know. You already know MA, you already know the enthalpy at every point, H5, H8, H2, and H3. You can just simply determine MB dot. Okay, so this is the flow rate of the refrigerant, okay, in the lower cycle or in cycle B. So this is the first answer. Okay, the first answer here. Now for the second questions, okay, we want to determine QL dot. QL dot is the heat removal from the lower cycle. Okay, so it will be just MB multiplied by H1 minus H4. Okay, and you can get the value of 7.18 kilowatt here. For Win would be the work required for compressor A and work required for compressor B. Okay, work required for compressor A would be MA dot multiplied by H6 minus H5. Work required for compressor B would be MB dot multiplied by H2 minus H1. Again, here you already know all values, okay, of every parameter. You can just substitute to obtain W net in is 1.61 kilowatt here. Now you can just simply calculate the COP of the overall Cascade refrigeration system. That would be QL dot divided by W net in dot here. And you can see that COP is 4.46, okay, which is quite high, okay, somewhat higher than you have seen before in the previous example of the simple VCR, which is around just 3.9 something. This is 4.46. Okay, now if you use the same condition, okay, between the highest pressure and the lowest pressure, and then try to calculate the COP of the simple VCR, you can compare the COP of simple VCR and the COP of this Cascade VCR. You can check by yourself. You find out that COP of this Cascade VCR will be higher than the simple one. Okay, and I guess that's all for the Cascade VCR and this illustration. See you next time for the part 5 of this lecture. Goodbye.